All right, so welcome to this session 7 of Canadian AI. So today we are in the session called Data Mining for Maritime and Biomedical Data. We are going to have 4 presentations. So the presenters will have around 12 minutes to present their work. Questions will be done in the end. So I strongly recommend that if you have questions, so you take notes. Once all these 4 presenters finish, then we can start a discussion, and then you will have the opportunity to ask those questions. If by any chance we don't have time, so you can always talk to the presenters, ask them to go together town, play a bit, right? And then talk to people, and you can engage there as well. All right, so without any delays, so the first presenter is Dogan Altan, and he will present the paper Discovering Gateway Ports in Maritime using Temporal Graph Neural Network Port Classification. So Dogan, from now you have 12 minutes. All right, please go ahead.
Okay. Thank you, Amilcar, for the introduction. So today I'm gonna present you our work entitled Discovering Gateway Ports in Maritime using Temporal Graph Neural Network Port Classification. So this will be the outline of my talk. I will make a brief introduction to the problem that we are addressing in this work, which will be followed by the notations that we use actually in the representation. Then I will explain the port classification algorithm that we implemented, which will be followed by the experiments that we have conducted to validate our methodology. Then I will conclude our presentation with some feature directions. So according to the United Nations Conference on Trade and Development, which was held in 2018, 80% of global trade actually has been operated by vessels and operated cargo activities at ports worldwide, which is actually a quite impressive number. And therefore, this makes it essential actually to ensure the efficiency of that navigation operations, because we know that they contribute to minimizing port congestion, and they also helps us to reducing vessels waiting time at ports or in some locations, waiting locations that I will briefly mention now. And they also helps us optimizing the usage of fuel consumption by these vessels. On the other hand, when we check the ACE data that we get from the vessels, actually, these auto identification messages, so we see that vessels actually often need to wait some specific regions outside the actual ports, the destination ports, actually. So in this study, we call them gateway ports, and they are not actual ports, actually, but they are some waiting regions for the vessels in the oceans or the seas. And there are several reasons, actually, why a vessel waits outside of the actual ports in the world. So the first reason may be the port congestion. So there may be some congestion on the destination port, so therefore it may not be available for that corresponding vessel at that moment to go there. So it needs to wait in such a case. Or the weather conditions may not be appropriate for the corresponding vessel, or there may be some issues related to the properties of the vessels or the ocean itself. So therefore, in this work, we are addressing the problem of actually discovery of these gateway ports in an automatic way, how we can actually detect these waiting regions that we call gateway ports. So here in this figure, we see a port region in Singapore. So we see some colored polygons on the figure. So these polygons are the results of clustering of these actual vessel data conducted by DB-scan algorithm. So on the right-hand part, we see the waiting regions where actually most of the time they wait. So higher density of the color means that the vessels are waiting there more. I mean, their visiting frequency is high on that regions. On the other hand, on the left-hand side, you can see the actual ports and the clusters where actually they wait because they are now in the port region, the actual ports. Now in this work, our task is actually to distinguish these waiting regions from these actual ports. So, of course, we know that vessel navigation are influenced by various factors. So we can categorize these factors under two categories. The first one is the dynamic environmental factors. That means they change over time. They are not static. On the other hand, we have also some static features that influence the vessel navigation, like the vessel type itself, the physical properties of the vessels, or the depth of the ocean, etc. And here I should note that to the best of our knowledge, state-of-the-art mainly concerns with the static features of the ports to classify these actual ports. So if I want to first summarize our contributions in this work, we actually present a novel representation that is actually able to capture spatial-temporal relations between these dynamic and static features of vessel trajectories. And then we present a novel temporal graph neural network-based methodology for discovering first and then classifying these gateway ports. And we experimentally show that actually our methodology that we present is able to detect and classify these gateway ports, which is validated on a real-world data set. So before briefly, I want to talk about the notations that we use in this study. So we have these automatic identification system messages, which is represented with tuple M. So in this tuple, we have the latitude and longitude information, and then we have the timestamp that represents the time actually that the vessel has transmitted that message. S corresponds to the vessel type or the identity of the vessel, let's say. And in this work, we use speed over ground. So of course, in AS messages, there are some other components, but as in this work, we only use these features that I only put them here. So we have port information, which is represented as P. It is again a tuple, so it has its ID and its center points as the latitude and longitude. Of course, we need to use a arbitrary function as well to define the port area, because the ports are not that a single location, so it's an area. So therefore, we use function gamma for that. So we consider the corner points of the ports to define this area. So we have, as a result, the trajectories of these vessels. So a trajectory of a vessel is actually an array of these locations that are transmitted sequentially. And a visit represents the existence of a vessel in a port area. So again, we have the port information, the message that has been taken on that visit, and the timestamp of it. And we have some voyages that represent the endpoints of these trajectories, discrete trajectories. So they are actually two, that corresponds to two visits. So there are some conditions for defining this voyage. The first one, the same vessel should should actually do these visits. And then the timestamp of the first visit should be less than the other one. So this should be earlier. So I would like to present our algorithm on this figure. So our algorithm has three main steps. The first one is the data preprocessing step. So we take the AES data, then first we preprocess this data. So the first step is the extraction of these nodes on the data. So we use the vscan to get the clusters in the data. But at this point, of course, we don't know whether they are actual ports or the waiting areas or the gateway ports, in another word. So the second one is the segment annotation step. So we annotate our segments in such a way that whether they have been obtained while they are in the port region or on the sea. And then we extract the voyages. So we have now the trajectories that the starting point is one port and the end point is another port. And then we construct our graphs. So here we are constructing a sequence of graphs. So as this is a temporal graph, so each graph actually corresponds to a day. So therefore, for example, for Monday, you have one temporal graph, the other day you have another one. So we construct these graphs. So then we train our model. So while training, we take into account attention mechanisms as well to see the importance of the neighborhoods. And then we process these sequences temporally. And then when we have a trained model, we apply or we can send some graphs to see the categories of these ports. So we use some features in our representation. So in our nodes, we have some port visiting statistics. We have the existence time of the vessels in that corresponding node, let's say, and then we have some speed statistics on that corresponding node. And on the edge, we have the voyage existence data. So that means, for example, assume that we have a graph of a single day. So if two nodes are connected to each other, that means there is a voyage, at least one voyage between these two ports on that day. And if there is a voyage on that day, we attach the distance of these two ports, the hover-shine distance, to the edge information. So on the right-hand side, we see the TGNN design that we use. So the first two layers are attention-enabled convolutional layers. And then we have a gated recurrent unit that can process the graphs as well, which is followed by a dropout layer. And then we have a fully connected layer to get the results. So in the experiments, we worked on 3 research questions, actually. The first question is related to the effectiveness of our method. We wanted to see how effective is our model in classifying the maritime ports. So I will show you some results for that. The second one is the effect of using spatial-temporal relations in our methodology. And the last one is related to training settings. So we will try to see how actually dropout probabilities affect the performance as a regularization parameter. So in our experiments, we used a real-world data set, which actually includes approximately 500,000 AS messages, which have been obtained from 10 vessels in a port region of Halifax, Canada. So it's 6 months of data. So while training, we applied time series split cross-validation, and we also apply early stopping to decide on when to stop training. So we have also some other hyperparameters. You can see them on the table as well. And if you are interested, you can just get the data set from this GitHub link below in the presentation as well. So about the first research question, we wanted to see the effectiveness of the methodology. So the first confusion matrix corresponds to the setting where we exclude temporality. We only consider graphs by itself without the other graphs in the sequence, and we try to do classification on that. So as you can see, the results are just a little bit better than the random setting because we have 2 classes. So when we include temporality, the performance greatly improves. So we have 88% accuracy here. And then if we both incorporate temporality and attention, we have 96% in classifying gateway ports. So let's then check the effect of spatial-temporal relations on these results. So alpha represents here the attention mechanism, whether it's used or not, and T is the for temporality. So here we show the results in terms of precision, recall, and F-score. So again, as you can see, if we exclude temporality, if we don't process the sequence temporally, we see that the result is at approximately 60% of F-score. But when we incorporate, for example, attention and temporality, we have a 95% of F-score in our data set. So we also wanted to see how actually the dropout does. I mean, which dropout probability should be used in our method. So we have seen that 20%, I mean, 0.2 probability as a dropout is better for us. It gives 95%. So therefore, in the experiments, we used that setting. So in conclusion, we believe that it's quite important to bring up this discovery of these gateway ports. and we provided a novel TGNM-based port classification method that processes spatial temporal data, and we have seen that on a real-world data set, our method achieves an F-score of 95%. Of course, there are many future directions for this work. So first, we are planning to analyze our proposed algorithm with a more extensive number of ports, which are located in different regions of the world. So right now we are working on the Halifax region. And we are also planning to give a more comprehensive comparative analysis with other baselines as well. And of course, in the long term, we are planning to process this detected gateway port information to optimize the trajectories of the vessels. So thank you for listening, and I'll be happy to answer your questions after all the presentations, I guess.
Thank you, Dogan. So as I said in the beginning of the session, so questions to the end. I have some, let's wait to the end. So now, thank you very much, Dogan. Doan. I forgot, sorry.
No problem.
So let's go with the second presenter, MD Mahbub. So yes, so you can share. Okay, so the second presenter is MD Mahbub from Dalhousie, and he will present the paper, A Clustering-Based Approach for Predicting the Future Location of a Vessel. So Mahbub, go ahead. You have 12 minutes.
Okay, is it okay if I put off my camera, because my network is a little bit weak, so.
No problem at all.
Thank you. Today I'm going to present our accepted paper, a clustering-based approach for predicting the future location of a vessel. This is my outline. So first I will discuss a little bit background, then I will present the problem of future location prediction and the proposed framework for predicting the future location. Then I will present some results, and finally I conclude this presentation. So we already know that from Doan presentation, maritime shipping is the backbone of global trade and manufacturing supply chains. And more than 80% of the global trade are currently conducted through maritime shipping. In addition to that, we also have passenger vessels, we have military vessels, fishing vessels. But in recent years, number of accidents in maritime domain has increased with the growing number of vessels, and mostly due to human error. So a vessel could avoid some accidents if a vessel knows future location or trajectory of surrounding vessels. That's why future location or trajectory prediction problem is very important problem. This problem is also useful for route planning and traffic prediction as well. But why clustering-based approach? We already know that clustering have been used by many researchers in many domains, and even in maritime domain, already researchers have used for vessel behavior analysis, traffic monitoring, route prediction, also for future location and trajectory prediction. But the current approaches have some limitations. For example, the current approach are not vessel type specific. So we assume that we already know that each type of vessel's behavior is kind of different. Also, we assume that if we use the trajectories of same type of vessel, then prediction model will provide more accurate prediction. Also, if we use mixed type of vessels, then then datasets should have to have enough representative trajectory for each type of vessel, which is computationally expensive. Also, in clustering-based approach, we need to compute the similarity measures among trajectories, which is also a computationally costly operation. On the other hand, current techniques only used K-means scan or Gaussian mixture model, and they are sometimes they have some limitation of finding cluster of variable density. Excuse me. On the other hand, we know that any vessel can be affected by wind and ocean currents in the ocean. So, but this technique didn't consider these measures. So that's why our goal was to reduce the computational cost and improve the prediction accuracy. So what we did, we proposed a vessel type specific model. So for that, model will be more focused in training so that it will provide more accurate prediction. Also, we'll get some computational advantage of using a smaller set of trajectories. And instead of using k-means or db-scan, we have used HDB-scan algorithm, which is efficient to find cluster in variable density regions. Also, to reduce the cost of similarity measures, we also use fast similarity measures, fast implementation of similarity measurement algorithm in our approach. And to address the ocean and wind currents, we introduced some new features like acceleration jerk, fog rate, bearing, and bearing rate in our approach. So to predict the future location, so the point from which we will predict the future location is, we call it target location, and the predicted location at time t+1 is we call it predicted location. So to predict the future location, we can either predict futures speed and course, then we can calculate the latitude and longitude, or we can predict the latitude and longitude directly. In our case, our two target variables basically future latitude and longitude. So this is our prediction model. This model consists of three modules, basically: dataset preparation, route clustering, and machine learning based prediction model. So in our first module, so we collected the dataset from maritime.gov of 1 month data. Also, we selected a geographical zone and extracted the data for that zone. Since vessel type is very important in our case, so we grouped all the vessel trajectories based on vessel type attributes, and then we combine the trajectory based on vessel attribute MMSI. Then we perform a set of pre-processing tasks in each of these trajectories. So first one is we remove all the AS message with duplicate timestamps. Since due to non-node settings of GPS software, sometimes clock values are appeared off. So we wrap the clock value to the interval 3 to 60 degree, 360. And since we need only moving vessel AS messages, so we removed all the messages contains zero shock value. We also remove trajectories if average shock value of whole trajectory is less than 1.5, because we think that maybe vessel is affected by wind or ocean currents. We also segment the trajectories into trips based on time segmentation. So if time duration between 2 points is greater than 60 minutes, then we divide into trips. Also, we set the minimum length of the trajectory at least 300 AS messages. In the second part, so we assume that similar type speed or course of vessels can follow or will follow the same route pattern. So we need to extract the routes from its geographical area of the target vessel. So in this case, we have used, already I said that we have used HDB-scan clustering. We also evaluated two widely used similarity measures, positive distance and dynamic time wrapping. And each of these cases, we have used Haberson distance as a distance function. But the main problem is we need to reduce the cost of computing similarity matrix. We can either reduce the number of points in the trajectory using lines trajectory simplification algorithm like Douglas filter, or we can also directly apply fast implementation of similarity measurement algorithm. So in our case, for prediction, we have used fast implementation of similarity measurement algorithm. Finally, to predict the future location, we already have a cluster database. So our first task is to identify the vessel type. And then based on the type, we need to find the nearest cluster of trajectories of same type. And we use this same type of trajectories to train the machine learning model. Excuse me. So in our case, we have used random forest and XGBoost to a prediction model. And we also build a supervised prediction model. In our case, future latitude and future longitude is the target variable. But we have used current values of current and previous values of latitude, longitude, and current values of shock, fog, acceleration, jerk, and other values to predict the future latitude and longitude. So this is some comparison between lines trajectory simplification algorithm or fast similarity measures. As I said, so if we look at the left side picture, this is a trajectory with 760 points, and after applying RDP, it's only just 261 points. We also computed the recorded the computation time of computing similarity matrix of 134 tanker vessel trajectories. And if we look at here for DTW, it's almost 4,000 seconds. And for after applying RDP, we need almost 3,000 seconds. But first implementation of DTW only require 424 seconds because there is a algorithm improvement also. So that's why we basically used first implementation of DTW for prediction. Now we have a database. So as I said, we need to find the type of target vessel. So in our case, we already have a vessel type attribute. So we use vessel type attribute here. So to find the nearest cluster of trajectories of same type, so what we did, we randomly select a point of the target vessel trajectory, and we use last 1 hour trajectory of the target vessel to find the nearest clusters. And for example, for this case, this is the nearest cluster of this target vessel. So we also have some results. This is the prediction result of 64 tanker type vessels. So as I said, we have used random forest and XGBoost. So both XGBoost and random forest provide better results with distribution clusters computed with Hausdorff distance. We also compare the results with 2 baseline. Second baseline, basically, in our case, we use all the trajectories of the nearest cluster for to train the model. But in baseline 2, so there are some models, they have used representative trajectory of the nearest cluster. So in that case, maybe central trajectory of the nearest cluster. So we also use the central trajectory. So in this case, if you look at, they are also provide better results with distribution cluster with Hausdorff distance, but compared to our method, their performance is poor. We also compare with very basic model, constant velocity model. Constant velocity model sometimes works very good if vessels goes in straight line, but other than it performance is kind of poor. But by looking at mean absolute percentage, it is very difficult to say the accuracy of the model. That's why we also calculate the Haberson distance between actual location and the computed location. So for example, average Haberson distance for random forest predictions is 544 meters with computed cluster with Hausdorff distance. But in case of dynamic timing is 635 meter. Excuse me. We also computed the Haberson distance for different time intervals for example, 5 minutes, 10, 15, and 20 minutes respectively. And we see that when the time duration increases, the prediction error is also increases. So we did the same experiment for cargo vessels, and we had the same results like tanker vessels. And finally, someone may ask about what about non-vessel type specific model. So we also compared our results with non-vessels. So for example, we combined the tanker and fishing vessel trajectories, and in that case, it was 281 meter, but in our case, it was 504 meters. So finally, I presented our proposed model. In future, we have a plan to add a deep learning model like LSTM. Also, fast forecasting is very important to reduce collisions. So we like to explore parallel distributed system like DAS in future. Thank you. And if you have any question, I will answer at the end. Thank you so much.
Thank you. Thank you very much, Mahbub. Just a bit over time, but we can manage. All right, so without further wait, so let's go to the third one. So Zachary, can you start sharing? Yes, that's great. So Zachary will present Preictal-Interictal classification for seizure prediction. So please go ahead.
Great, thank you. So My name is Zachary Georges Yap. I'm an MASC student under the close supervision of Dr. Milos Popovic and Dr. Shiraz Khan at the University of Toronto. Today, I'll just be presenting my work, which is Preictal-Interictal classification for seizure prediction, specifically on continuous intracranial EEG. So, epilepsy is one of the most prevalent neurological disorders in the world. It affects around 50 million people worldwide and over 140,000 people in Canada alone. The majority of cases of epilepsy, about 70% of them, can be treated using anti-epileptic drugs. However, the others cannot be treated long-term at all. So these people have to live with the main symptom of epilepsy, which are seizures. So epilepsy is characterized by these uncontrollable and unpredictable seizures. There's a lot of potential injuries that can arise from having a seizure. For example, you can have a head injury or a fracture from the falling or from the convulsions themselves. You can also just get an injury while trying to perform a basic activity and then having a seizure, like having a seizure while driving or cooking or ironing, and then having a seizure could lead to a burn, for example. What's more is that 16% of people with epilepsy end up dying during an epileptic seizure. And on top of all of this, just the unpredictable or the seemingly unpredictable nature of a seizure causes significant stress in a patient's life, not knowing when their next one will occur. In fact, a study found that when surveying people with epilepsy, their number one reported negative impact was the unpredictability of their seizures. The majority of work in this field is on seizure detection, which is very useful for the identification of seizures and the diagnosis of epilepsy, but it's not very useful for managing seizures on a day-to-day basis. If we can predict the onset of a seizure, we can either take precautions to reduce injury or just treat the seizure before it happens and prevent it altogether. Some potential treatment options include fast-acting anti-epileptic drugs or functional electrical stimulation. And above just treatment options, being able to predict the occurrence of a seizure will alleviate a lot of the stress and uncertainty that people with epilepsy feel. The most common modality for seizure prediction is electroencephalography, also known as EEG. It's used by epileptologists to identify seizures, to diagnose epilepsy, and to treat patients. There are two main types of EEG. There's scalp EEG, where electrodes are placed on the scalp, and intracranial EEG, where electrodes are directly implanted into the brain. Typically, scalp EEG is noisier, but obviously it's significantly less invasive than intracranial EEG. However, for my seizure prediction work, I will be using intracranial EEG, mainly because of its superior sensitivity. To be able to predict the onset of a seizure, we have to first understand different stages of a seizure. So this here is just a plot from the database I used in this work. We have 4 different states of a seizure. So in green, the smallest part here is the ictal state, which is just brain activity during a seizure. In blue, we have the interictal state, which is just regular brain activity, which isn't at all associated with a seizure. In orange, we have the preictal state, which is brain activity directly preceding a seizure. And then after a seizure, we have the postictal state, shown here in red, which is typically around 30-ish minutes. So the idea here is that by identifying a preictal state, we can assume that a seizure will occur within some given time. So we can view seizure prediction as this classification problem between the interictal and the preictal states. This preictal state is considered a time period before a seizure where there are some kind of observable physiological changes. One issue is that the length of the preictal state is not agreed upon widely in the scientific community. A recent study used statistical analysis to investigate what the optimal length for the preictal period could be for seizure prediction. They found optimal prediction periods ranging anywhere from 5 minutes all the way up to 173 minutes, with an average about 44 minutes. And what's more is that They also found that this optimal prediction period varies on a per seizure basis, even within the same patient. This means that without seeing the data beforehand, it's basically impossible to decide what the optimal Preictal period length should be. And this is a big problem for a machine learning application where we need to make some kind of assumption on the Preictal period length before we begin. So the best way to do this is likely to decide empirically based on our in-sample training data. Another important data parameter is the distance from a seizure at which we select interictal data. For example, here, the study below only selects interictal segments that are at least an hour away from the onset of any seizure. Ideally, we should be able to correctly classify interictal data, even if it's close to the start of the Preictal period. And when we have this large interictal distance, what we're doing is we're really artificially increasing the separability of interictal and Preictal states. And a lot of studies have this interictal distance, but don't provide a good reason for why they do this or any reason at all. And sometimes these interictal distances can be hours or even days, or sometimes I've seen studies that have used interictal distances of a week long. So this leads me to my research question. Can we accurately classify Preictal and interictal samples that are in temporal proximity on long-term continuous data? The database I'm using here is the Sleep-Wake Epilepsy Center and ETH Zurich Intracranial EEG database. It's a database containing continuous recordings from 18 patients with over 2,500 hours and 100 seizures across these patients. It's publicly available, and the reason I chose it is that it's a raw data set, so I have a lot of control over the data parameters I choose. One of these data parameters is the window size. The first step in processing our raw data is to break up our data into samples using this window size. The window size is simply the length of EEG in seconds defined to be one sample. In this example here, it would have been 5 seconds. We can also overlap these windows if necessary if we want to artificially generate more data. This is just a quick overview of my data processing pipeline. First, we segment our data into samples of length window size. Then we label each sample as either interictal or preictal based on our criteria. Then we perform a time frequency transform, in this case, a short time Fourier transform on each of our samples to get this two-dimensional image. Then we pass these samples into our model, which is a really basic CNN, which is good for image classification. Another important thing to note is that only seizures that are 4 hours after a previous seizure are considered to be lead seizures, and other seizures that don't meet this criteria are discarded. This is mainly done to ignore cluster seizures, where seizures occur in close succession, because when we have a cluster seizure, it's really only important that we predict the occurrence of the first seizure in the cluster. This is pretty common practice across a lot of different studies. The standard way to partition our data set would just be to randomly assign samples to either a training set or a testing set with some fixed ratio. One issue with this partitioning method for seizure prediction is that we would be taking interictal and preictal data from all our available seizures. So we'd be training on partial data from all seizures, preictal and interictal data. What this might do is it might cause our results to be overly optimistic, and we will not know if our classification will generalize to a new seizures preictal and interictal data. So instead, we choose to use something called leave one seizure out partitioning, where the last seizures preictal and interictal data is used as the test set, and the other seizures in the set would be used as the training set. This is done so that we can test our model's ability to generalize to a completely unseen seizures data. And then, of course, we would only look at this test set once we've decided on the final model and data parameters. Here's just basic data attributes from the patients I've currently experimented on. In the number of seizures column, you could see that in brackets is the number of lead seizures. So you can see that for a lot of these patients, we had to discard some of the seizures because they were too close to other seizures in the set. So what I've done is I've run experiments to evaluate the performance of my architecture across changes in data hyperparameters. I'm looking at changes in both the window size and the preictal period length. I'm looking at window sizes of 5, 10, 15, 30, and 60 seconds, and Preictal period lengths of half an hour, 1 hour, and 2 hours. To decide these hyperparameters for each patient, I use a cross-validation, where my validation set is another left-out seizure from the remaining ones in the training set. And you can see that the test set would be completely excluded from this process. To evaluate the performance, I'm using area under the ROC curve, AUC. So using my optimal hyperparameter configurations for each patient found in my tuning experiments, I ran my model on the test results. So you can observe that for some of the patients, I got good test performance, and it's very comparable to the validation performance. And this is a trend in general. For almost all the patients, the validation results are very close to the test results. So this is very encouraging for the methodology. So if my validation results are bad, then it's likely that my test results will also be bad, and vice versa. So this means that my methodology provides a good indication for whether my model will generalize to a new seizure. One important thing to note is that these test results are only evaluated on one seizure's Preictal and Interictal data, so there may be a lot of volatility. So overall, the results look promising, and we've achieved good prediction performance on some of the patients. The encouraging thing is that the leave one seizure out partitioning combined with cross-validation provides a good indicator for the model's performance before even looking at the test data. One issue is that, as I said, we're only testing on one seizure's Preictal and Interictal data, so it's harder to provide a higher confidence in the results. That being said, it would be nice to have more data per patient, especially more lead seizures per patient. Then it would be possible to have a test set with multiple seizures and also have more training data in general. In the future, I'm going to continue to try newer architectures, since this was mostly an initial work with a fairly basic architecture. I'm looking into trying temporal convolutional networks, as well as a CNN-LSTM hybrid network. I'm also looking into trying an unsupervised approach, like anomaly detection, where I fit my model on only interictal data and detect anything anomalous as an alarm. This would help with the problem of not having enough preictal data. And that's all. Thank you very much. And I'll be here to answer questions after all the presentations are done.
Thank you very much, Zachary. So let's go to the next one, and congrats. Very nice work. All right, so the next one is Hirad.
Oh, sorry, I had to change the room. Sorry about that.
Okay, no problem. So go ahead, share your presentation.
Okay, so you can see my screen, right?
Sorry? Yes, we can see that.
Okay.
All right, so the next presenter is Hirad Daneshvar. So he will be presenting the paper Heterogeneous Patient Graph Embedding in Readmission Prediction. So go ahead, you have 12 minutes.
Thank you. Hello, everyone. My name is Hirad. I'm a PhD student in the Department of Electrical, Biomedical, and Computer Engineering at Toronto Metropolitan University. I'm happy to present to you our work on heterogeneous patient graph embedding in readmission prediction. Accurate hospital readmission prediction is beneficial both for the patients and for the clinicians. For the patients, it helps maintain their health status, and for a clinician, it will improve service allocation. However, this is a challenging task, especially in the mental health domain, as visits to ED may occur without a clear connection to their mental health status, and the services the patient utilizes can be diverse, causing heterogeneity in the data associated with each service. There is a growing interest in using deep learning in readmission prediction by analyzing health records. So this is a sample health record. So this is ED admission example. So here the data contains patient's age at the time of visit, triage level, visit disposition code, services utilized, and the most responsible diagnosis code. Each record feature can be divided into 3 categories. The one with the orange rectangle around it, there are visit features. The green one is the service utilization features, and the blue ones are the diagnosis features. Also, 3 types of connection we can extract from these. We can extract visit connection, visit service, and service diagnosis. EHR data that have complex structures that can be represented using graphs. So when using graphs to represent data, the structure of features and their interrelationship can be captured by using nodes, edges, and directions. As you can see on the right, the orange nodes are our visit nodes, which we extract from this portion. The green ones are our service utilization data, and the blue nodes are the diagnosis data. Graph neural networks, or GNN, have shown promising results in classification and regression tasks using these data. Multiple GNN and recurrent neural networks have been proposed to process EHR data. However, most GNNs do not consider heterogeneity of the data. So the nodes and the connections are treated the same, so they're homogeneous. So as you can see on the right, compared to our previous slides, they're all in one color, meaning that they're all treated the same. They're all the same, no difference. The ones that consider heterogeneity, they mostly are used for node classification and node regression, not graph classification. And RNNs, they naturally cannot utilize the interrelationship between features of the data point. So we developed heterogeneous patient graphs, and also we propose a network that first performs separate pooling operations on nodes of each node type, then aggregates these pooling results to create the final graph representation. And finally, we compared the proposed method with RNNs. So let's first talk about the heterogeneous patient graph. So 3 node types have been added for each patient. So this is a single patient's data. So we first extracted visit features, which are patient's age, triage level, and visit disposition code, then service utilization features, which are the service data, and diagnosis features, which are the diagnosis codes. Then we have the edge types that are visit. So visit A to visit B, which shows that visit B happens after visit A. Visit service, which shows service C was utilized during visit B. And service diagnosis edge, which connects service C to diagnosis D, for example, shows that patient was diagnosed with D while utilizing service C. So this is our same patient data. So this patient has 5 visits, as you can see. So we first extracted those 3 node types. Then we created our patient graph. As you can see here, this is a heterogeneous patient graph with different types of connections and different types of nodes. So yellow nodes are all visit nodes, service nodes are all in green, and diagnosis nodes are all in blue. And this is a directed graph, as you can see. Now let's talk about the network. So basically in GNNs, they first need to extract the node representation or node embedding. This is done here using graph operation layers. They extract node representations from each node and its neighbors using the adjacency matrix and node feature matrix. So on the right, we have 2 model structures, one with 1 layer of graph operation, one with 3 layers of graph operation. So we need to aggregate these representations to create a graph embedding. So first we have node embeddings. We have to aggregate them to have a graph embedding. Most models use a global mean pooling layer, like what you see in CNN, so the green ones here. And then they use this result of the global mean pooling layer as the graph representation, and they use it for the classification. What we did was, in order not to risk losing important information regarding node type, in each layer, we calculate the embeddings using separate mean and max pooling layers for each node. Then we use the graph representation to do the classification like before. So here, after each layer, we have a pooling layer. And if we have more than 1 layer, we need a pooling summation to create our final graph embedding. I will show the internal of the pooling layers just in a second. And in our experiments, we used the graph transformer operation as our graph operation name. So this was our 2 models. As I said, after each graph operation layer, we have a graph pooling layer. And if we have more than 1 graph operation, then we need a pooling summation in the end. So because these are all the same, we will just pick one of them and look into that. So as you can see here, we have 3 types of nodes: visit nodes, service nodes, and diagnosis nodes. For each of these representations, we separately calculate or use a mean pooling, and we also separately use a max pooling. Then we just have a pooling summation only for mean pooling layers and a pooling summation for max pooling layers. Finally, we concatenate these two and create our final pooling layer result, which is used here for classification or here as summation, then using for classification. Now we want to compare our method with RNNs. So we use real-world mental health patient data provided to us by McMaster University. We evaluated our models for the following tasks. Task 1 will be will the patient be readmitted within 30 days of discharge, which is a classification task. Task 2 is how many times will a patient be admitted to ED within 90 days of their mental health encounter, which is a regression task. And task 3 is if we know a patient will be readmitted, how many times will the patient be admitted to ED within 90 days of their mental health encounter? Again, this is a regression task. Then we wanted to compare our model with RNN models. So we used a bidirectional LSTM with one layer of bidirectional LSTM, BiGRU, and our proposed GNN with only one graph operation layer. So we wanted all of these to have the same structure. For task 1, will the patient be readmitted within 30 days of discharge? So the data is imbalanced. We have 767 readmitted patients and more than 3,700 patients not readmitted. So we trained our model 5 times. Each time we kept all the 767 data points with label 1, and we randomly selected the same number of patients from the ones with label 0. Then each time we did a 5-fold cross-validation. So as you can see on the right, our GNN has slightly better performance and accuracy NF1 score than RNN models. The improvement is not a lot, because the way we handled the data imbalance caused us to lose some of our data points. For the second task, which is how many times will a patient will be admitted to ED within 90 days of their mental health encounter, we used all patients with at least one ED admission prior to their mental health encounter. And as you can see, the average root mean squared error for the GNN is nearly half the root mean square error for the RNN models, which is a good improvement. Also for the second task, which is similar to the second task, but we say, if we know that the patient will be readmitted, now how many times will that patient be readmitted within 90 days? So again, we use the same patients. So patients with at least one ED admission prior to the mental health. However, because we want to make sure that the patient has been readmitted, we only use those that have at least one readmission within 90 days of their mental health encounter. Here again, our average root mean squared error is close to half the RMSE for the RNN models. Again, so this is a good improvement. So RNNs are not naturally capable of utilizing interrelationship between features. Most GNNs either do not consider heterogeneity of the data or are only targeted towards node classification or node regression. Heterogeneous patient graphs were extracted in our study for EHR data, and a GNN network was devised to process them and create graph representation, taking into account that the nodes are, or the graph is a heterogeneous graph, so taking the heterogeneity into account when creating the final graph representation. Experimental evaluations demonstrated that this approach can improve outcome prediction performance for sequence analysis compared to RNN approaches. In the future, we want to extend our model by using different graph operators for different edge types. Because we have different node types, the graph operator that we can apply to them to create the representation can be different for each edge type. And also, we want to fuse more diverse service utilization data, all for the same underlying health problem. Thank you once again. I'm Hirad, a PhD student at Toronto Metropolitan University. Thank you for listening, and I will be glad to answer any questions if there are any.
Thank you very much, Hirad. All right, so let's go. We still have around 10 minutes. So let's do a round of questions for each presenter. So let's start with Dogan. Dogan, someone has a question for him? All right, Renata, go ahead.
Thank you, America. Thank you, Dogan. I have a quick question, and it's because I may have missed something from your presentation. So when you say port gateway, you're considering the port, but also the anchoring sites near the port, right?
Yeah.
Is there?
Yeah. Please go.
So is there any other entity? So it's the anchoring site near the ports and the ports itself, or if there is any other, maybe an anchoring site that does not belong to a port or it's not a newer port?
Yeah, exactly. Thank you for this very nice question. So in our work, we have two class types. So the first one is the actual ports that we know that they are ports, they have facilities, etc. But on the other hand, for the gateway ports, we are referring to the areas. Actually, they are not actual ports, they are not physical ports, but they are some waiting regions. But this can be for several reasons, for anchoring, for weather conditions. The vessel needs to wait there, etc. So the distinction here in this work actually is being an actual physical port and the other waiting areas. It may be, as I say, due to many reasons.
Right. Oh, thank you. And why did you not consider, for example, distance to shore? Seems to be a very discriminative feature, right?
Yeah, but yeah, you're right. But there are also some waiting areas that are really close to the ports as well. And these areas are dynamic. So there are no actual definitions or locations for these vessels. They always change dynamically month by month, even for the season as well. So for each season, it may be changing. So that's why we wanted to actually address this problem in an automatic way. To learn actually the patterns, the spatial temporal relations actually in the AS messages rather than that. Thanks for that. It's my question.
Thank you.
I hope this could be an answer to your question.
Yeah, thank you very much.
Thank you.
All right, thank you, Renata. Let's make a question for the second presenter. So MD Mahbub, any questions? Okay, so I can make a quick question. So it was not clear to me, Mahbub, eventually you said that you consider wind and currents, but I could not see how you were adding these to your modeling, or maybe I misunderstood what you presented.
Yeah. So we introduced some features like acceleration, jerk, bearing rate, cog rate. So basically, when vessel affected with wind or currents, then we train the model using these features, so that even vessel speed or direction is affected by wind or currents, so that prediction model can predict correctly. So that's why we introduce these features. So basically.
Okay, so basically you were using kinematic features, features, right? Regarding the motion. Okay, so one just quick thought when I saw your validation. So have you considered, for example, using as a baseline the trackless algorithm in a way that you could kind of extract a more meaningful route from that cluster? And this could be kind of a baseline for you to compare how far from that cluster your new technique is. Maybe this could be a good baseline, because that paper has 3,000 citations and so on. And it's a clustering based technique as well. So.
Yeah, you're absolutely right. I can do that. But since we are using HD-DBScan algorithm, so trackless basically developed based on DBScan. So the main limitation of trackless is the limitations of DBScan itself. So that's why, since I already used HDTV scan for clustering, that's why I didn't use compare with Traculas. But yeah, I can do that. You are absolutely right.
Yeah, it's just something to consider because it might be a good baseline.
Yeah,
right?
You're absolutely right. Yeah.
All right, so let's move to one question to Zachary. Questions for Zachary?
Hi. Sorry, let me adjust my camera. So, quick question, Zachary. I noticed and you discussed actually the issue of the length of Preictal time, which varied from a few minutes to several hours in the literature. And you experimented with all of those. I'm wondering if that's really something you should be optimizing, or if you're if this is due to the differences between patients, between people, so different people react to conditions in different ways, in which case the length would need to be adapted to each person rather than optimized in your architecture. You would need, of course, a lot more patient info, more detailed patient info to do that. I'm wondering if that might be the case, if this is something in the literature, something you consider.
Yeah, no, that's a great question. I don't know if I guess I don't think I made it very clear, but these models like were patient specific. So I was trying to look for an optimal preictal period individually for each patient.
I hadn't gotten that, but all right, then thank you for clarifying that.
Yeah, sorry. Yeah, I hope that answers your question.
All right. Any other questions for Zachary? No. So I just have one quick comment. The way you did your validation with your patient data, so the way you use it cross-validation, I'm not sure if this is kind of the best way, because imagine that you are using maybe I'm wrong, but you just got something that happened in the past, and then you used some data that was in the future, and then you trained here, but then you are trying to forecast something that came before. Am I saying, have I understood correctly how you did your validation?
Yeah, no, you're correct in that. So
okay, there is one strategy that might be better for you, which is pretty much, I forgot the name, but it's pretty much, so you have that big window, so you can randomly start with some training data here and then forecast a bit kind of in the future. And then for a second round, you randomly start somewhere, right? And keep doing that and generating as many estimations as you can. In that way, you are not using data from the future to prevent events from the past.
Yeah.
Right. So that might be a better strategy, I believe, for this type of data.
Okay. And
I'm sorry, but I just forgot there is a name for that, for that type of validation.
Okay, I'll look into it. That sounds
okay.
Good.
Good.
Thank you.
All right. So at least one question for our last presenter, for Hira.
Yep.
All right, Renata, go ahead.
Thank you. So my question is, you have created a node embedding for each node type, right? And then you merge them all together at the end. That is the architecture, right?
Yes. So first for each node type separately, then because I wanted a graph embedding, then I had to aggregate them all together. That is what. Yeah. Sorry. Go ahead.
Oh, no, go ahead. Sorry. Go you first.
So instead of just doing a global mean pooling like what we can see in CNNs, for example, we have a pooling layer for each node type separately. So for each node type, we have an aggregated result. Then we did a summation. So in this way, we don't, if we do a max pooling, for example, a global max pooling, we may lose some information of some of those node types. But in this case, because we did a max pooling and a mean pooling separately on each node type, and then we just had a summation of those, we kept the information for each of our separate node types.
So one node embedding for one type would not have a higher weight in
yes,
right?
Yes, they're all the same. So we don't choose one over the other.
All right. Okay. Thank you. Understand. Thank you very much.
Any other questions? All right. So Hirad, thank you very much. We just finished this session 7. So I have to check what comes next. But so Ilujo is here, so probably.
Yes, I'm here.
Yeah, okay.
So next we have the keynote.
Keynote
At 12:30. And Mark, that you see there, is going to chair the keynote.
Yeah, be David Poole from University of British Columbia. So come back in 15 minutes.
Please go ahead.
Yeah, we have a 15-minute break, and then I will see you back here at 12:30 for that.
Thank you, guys. Bye-bye.
To say, oh, great. Now we're recording, so we'll start introducing as people kind of filter the ways in. I'm Mark Crowley from the University of Waterloo, Electrical and Computer Engineering Department. And I'm excited today to be in charge of chairing the keynote talk for today's AI conference on our Australian keynote day, apparently. So CRV just had their keynote talk from Peter Cork, so it was great. And so now AI has David Poole from the University of British Columbia Computer Science. And David Poole was my PhD supervisor. So I'm familiar with all of his things, and I was there, joined in 2003. And he never disappoints to give introducing new ideas, thinking outside the box and very long-term horizons and ideas for AI research. His focus is on researching combining logic, probability, probabilistic inference, statistical relational AI, semantic science, and more. He's the author of 2 or 3 textbooks, depending on how you count them. I think the revision of the AI textbooks kind of coming up again soon, so that's great. And he's the former chair of the Uncertainty AI Intelligence Conference, or UAI, as well as winner of the Kayak Lifetime Achievement Award in 2013. And he's a fellow of AAAI and Kayak. And today he's going to be talking about big pictures and probabilities and AI. So I'll leave the floor to him, and we'll have good questions afterwards. So.
All right, thank you, Mark. All right, I'm glad to be very pleased to be invited here. All right, so lots of people give talks these days. They say, I have my new hammer, and now this new hammer is really good on all of these nails. And then you look around, and the trouble is for new students coming in, as they sit there and wonder and thinking, oh my goodness, these new hammers have solved all the problems. So what I'm going to do today is I'm going to give a different story. What I'm going to try and do is to talk about the problem, and then talk about why none of the hammers so far actually solved this problem, and why therefore it's such a good field to go into, why it's such lots of interesting things going on. All right, so why you should be interested in this. So I started off, I had this quote from Steven Pinker I did, and what I want to highlight here is that the mind is a neural computer fitted by natural selection with combinatorial algorithms for causal and probabilistic reasoning about plants, animals, objects, and people. And if you think about much of your learning in machine learning, it's not really about plants, animals, objects, or people. It's not about things. It's about text, or it's about pixels, or it's about photos or videos, right? Whereas somehow humans and high-level reasoning seems to be, it seems very strange to me that we're not talking more about plants, animals, objects, and people. All right. Since the outline of this talk, there's lots of overview of lots of problems that exist, and some of this is sort of more tutorial, and some of it's trying to say, what it is that we can't do. All right, so we're going to start off talking about relational models. So here's the motivation. So AI studies what agents should do. And the argument is acting is gambling. Whenever an agent acts in the world, they're gambling, and agents who don't use probabilities will lose to those who do. And you should never believe a definitive prediction. If someone tells you you will run over tomorrow, do not believe them. So if anyone gives you a definitive prediction, do not believe them. The only predictions you should give are, if you're careful, the probability is this, and if you're not careful, the probability is that. Do not believe someone who gives a prediction without quantifying that prediction. And if you look at what's the world made up of, if you look at the machine learning literature and the probabilistic literature, they'll tell you the world's made up of features or random variables. But similarly, everyone else, the world's made up of things. There are entities, there are individuals in the world, and they have properties and their relationships among them. Okay, so one of the ways we've been doing it is, so there's talks about how to reconcile these. And one of the things we've been doing is these sort of relational probabilistic models. So from a logical point of view, you could start off with propositional logic. You could add relations and logical variable and quantification and get the predicate logic, or you can add probability, and we want to add both. We're not content with just having probability over propositional logic or just having predicate logic with no uncertainty. We're interested in making probabilistic predictions about entities and relations. All right. So a common thing that people go on is knowledge graphs. So this is, so let's look at those. So here, so if you look at introductions to AI machine learning, they start with learning from relations like this, right? You have this author and there's all these different values down there, and you try to predict one of these values from, you try to pick what the user is going to skip or read this article, try to predict user action. It turns out that no real data set is like this. What they're really like is that there's lots of meaningless names inside of it. There's student numbers, product IDs, user IDs, or movie IDs. So here's one of the simplest relational models. This is the movie lens 100K. This is the first 2 items on it. And it says user 196, and it's just an arbitrary number for this user. And movie 242 had a rating of 3 in this timestamp. And there's actually information about the user in other relations and information about the movie in other relations and indexes into IMDb, etc. But these names are arbitrary and can be changed or exchanged with exactly the same meaning. All right. So now let's have a look at representing relational things. We could represent in sort of logic, we could represent how to represent pen number 7 is red. So we could represent a relation. Pen number 7 is red. We could write color. We could write pen 7 is red. We could write the color of pen 7 is red. Right? This one here actually has better. You can ask more things. You can ask what's the color of pen 7, where in the first one, in a first order logic, you can't. And you can keep doing that again. You get to prop. You can write prop of pen 7, the color is red. Now it turns out that you don't need to keep doing this again, because a single relation is all we need. This prop is all we need. There's just triples. Pen 7, color is red. Turns out that all relations can be represented in terms of triples. Okay, so here is a table. Here's a typical table with a row, property, and a value. Can be represented as this triple of R, P, and V, the value of at row I and column V. And so either Ri is a primary key or a reified entity. It's something that's made into an entity. Okay, and examples of reified entities are a booking. You can talk about a booking, a marriage. They're relationships amongst things we've made into a thing and often given a name. All right, so these are often called semantic networks, entity relationship models, or knowledge graphs. So once you have this, it becomes you can draw it as a graph. So here's an example of a graph. So this is an example of the Wikidata entry for the great Cameroonian soccer player, Samuel Eto'o. And Samuel Eto'o is Q1255624. Okay, and the name of this person, the name of this entity is Samuel Eto'o. Samuel Eto'o is not the person, that's their name. They have a date of birth. They're a citizen of 2 countries. There's this Q29, which has a number of names. In English, it's Spain, and in Spanish, it's España. Sorry about my pronunciation. And there's a reified entities here. So it turns out that Samuel Ito played for FC Barcelona, which is Q7156, from 2004 to 2019 and played 144 matches. All right, that's part of how Wikidata is representing things. They have these reified names inside it. And if you look inside a relationship, a lot of the entities are like this. In fact, most of the entities in Wikidata are like this. And there's very few facts about them. All right. Now, it's actually pretty dangerous to just translate into triples. So people do things pretty. So for example, Air Canada flies from New York to Vancouver, and Air Canada flies from Vancouver to Los Angeles. Okay. So you can think of the triples. Air Canada flies from New York and Air Canada flies to Los Angeles, but this is lost information because Air Canada does not fly from New York to Los Angeles. So if you don't reify, if you don't sort of make up a flight number, for example, and you just project, you actually lose information. So we have to be careful doing that. So here is here's an example I'm going to use a few times. So here's a FB15K is a knowledge base used in lots of research papers as comparing things. It's from an old Freebase, which is a precursor to Wikidata. And here's one of the triples that's in the test set. Jade North, well, of course, they use their actual number for Jade North, plays position defender. So Jade North plays position defender. And another triple is Derby County Football Club has position defender. Okay, and both of those use meaningless names, but then it wouldn't make any sense to you at all. Okay, so these are test sets in this triple. Okay, and again, this is made up of the case of we've ignored the reified entities in doing this. It's tripled by ignoring reified entities. So it loses information, but we'll do that. It does this for a reason, is because their hammer, the people who's been using this, the hammer that they're using, doesn't really work on reified entities. Okay. Now, if you look at lots of machine learning current literature, they'll tell you about words as vectors, right? You can say, oh, it's really good because king minus man plus woman happens to have the similar embedding as queen. Okay. So it's tempting to want to do in what's called translation models. The Brussels is Belgium plus the capital of, and Ottawa is Canada plus the capital of. And you can view these as vectors, and it works, seems to work well in natural language. However, this entails that Canada is just Belgium minus Brussels plus Ottawa. And I'm willing to bet that if I tell you everything you wanted to know about Belgium, everything you know about Brussels, and everything you knew about Ottawa, you still couldn't tell me anything non-trivial about Canada. Okay, so having this doesn't really necessarily seem sensible for people who've tried to put this in. It's sensible for dealing with entities. Because basically words have simple meanings and almost all entities are multifaceted and complex. You know, it's a very tiny part of Canada is the fact that its capital is Ottawa. And the other issue about vectors is that the question is, should we use the same size vector for Canada as for this other one, which is the contract between Samuel Ito and FC Barcelona? And it seems as though, you know, fixed size vectors aren't going to work for us. All right. So let's talk about now learning knowledge graphs. All right. So here's an aside of some of the people know this very well and some people don't. And so I want to do it. Just as a quick aside, the probability of the hypothesis evidence is Bayes' rule. You can write it in this form here. You can divide the top and the bottom by the probability of H given E is 1 over 1 plus that. And you can put it in this, and you can exponentiate a logarithm and do the exponential of the logarithm. Okay, and this is called the sigmoid of the log of the odds. Okay, so often we introduce sigmoid just arbitrary, but what we're going to view is that sigmoids lead to probability. If you want probabilities, you use sigmoids. Typically then the odds formula, this log of odds formula, odds is a product, and so the log of odds becomes a sum. And so you end up with the odds as a product to get the sigmoid of a sum, which is called logistic regression. So in the models I'm going to give, if I ever want to get a probability of a Boolean variable, I'm going to use logistic regression. I'm going to add a sigmoid to it. If I have just a discrete categorical feature, I'm going to do the softmax. I'm going to put softmaxes and sigmoids. If you wonder where they come from the fact that we want to predict a probability because we want to make decisions in the end. All right. So here's a standard way, it's a binary relation like likes person movie. And so here's a typical way to do this. And this is in pseudo-Python. So what happens is an embedding for the person over these features, and there's an embedding for each movie, and we sum product over the features. And this, of course, is the matrix multiplication, where the embedding for the person and the features is, this is the embedding for the person, and this is the embedding for the movie. So there's a movie embedding and header embedding. I wrote this in a weird notation for people who are interested, who are used to matrices, right? So matrices people wouldn't write it like this. I'd use matrix notation. But I wanted to write it like that is because if you look at it this way, if you want to think about to learn a triple, well, instead of multiplying two things, the obvious solution is you want to multiply three things. So here is the same thing before. So instead of multiplying two things, we're going to multiply three things. So there's the embedding for the head, the embedding for the R, and the embedding for the T, and there's sort of a three-way version of the dot product, right? If you've been indoctrinated into matrices and vectors, you might not like the three-way one, but for those of us, but for some of us, this is obviously the most natural solution to this. It's called the Polyetic Decomposition. It's from 1927, and there they weren't so, people were very happy to talk about, to talk about, higher order tensors. Right, this is the Polyetic tensor decomposition. So tensor is just this triple here. All right, and then this one here has two vector embeddings for each entity, one when the entity is in the head and one when the entity is in the tail. And there's one for each relation. Okay. If you try this, you find it doesn't work very well. It seems like a good idea, it doesn't work any well. Here's why it doesn't work very well. Consider that person 123 likes movie 53, and movie 53 is directed by person 534. Okay. Now, what happens in the Polyetic decomposition is there's an entity of P123 when it acts in the head, sorry, an entity for M53 when it acts in the tail, an entity and an embedding for M53 when it acts in the head. And these two embeddings are just completely independent of each other. And so you can't actually learn that P123 likes movies directed by P534. You can't learn that because you can't actually represent it. All right. There are a few solutions to this. So dist-mult shares the same embeddings for the head and the tail. That implies that relations are symmetric. Complex is like dist-mult, but the embeddings are complex numbers, and the tail is the conjugate of the head embedding. My favorite is simple E. Basically, we have an embedding for the inverse of R to the -1, and to learn to predict both the head triple and the inverse triple. And the inverse triple, of course, uses R to the -1, and then these two can share embeddings. Complex and simple are actually quite very closely related. But what a version I like is simple plus, which is simple with non-negative entity embeddings. And the reason I like it is that I can explain exactly why it works. So I know exactly, I can explain why that works, and that's the next slide. You can represent arbitrary relations. If you give me an arbitrary relations, I can represent it in this. And point y is less than corresponds to implication. So when we first did this, it was the point y is less than was the implication. But the reason I did this, reason I like doing this, reason I like this simple plus model is that I can explain what's going on. All right, here, let's go this. So I have this triples, you're multiplying three things together and you're summing them. Well, the only things that matter, things that, if this is approximately 0, it doesn't matter, right? So this is approximately 0 if any of them are approximately 0, right? So the 0 ones, we can sort of ignore these ones. The things that are remaining are the ones where they're all away from 0. Okay, so the ones where this is the only ones we really need to worry about are where this is, way above 0, because the zeros just get washed out. They're just irrelevant to us. Okay, and so now what we have here is that all of them have to be above 0. So what happens now is that this feature, this ith feature, the ith embedding position, forms 2 clusterings, right? It forms those entities for which the first clustering is high. It's a soft embedding of entities. So it's a soft clustering of entities. It's those for which this is high and those for which the third position is high. Okay. And the entities in the first cluster relate to the entities in the second cluster, for any relations in which the E1 of Ri is true. Okay, so if the relation in that position is high, then they're related. Otherwise, they're not. So basically, we're having soft clusters of entities, and one soft cluster is related to another soft cluster, and the relation picks out which clustering we're going to use. The negative values for E of Ri provide exceptions to, so it's generally true except for this exception. So you can have exceptional representations. Okay, that was probably the most dense slide I have. All right. Now, let's suppose we want to construct a model of who is friends with who. So now we want to construct a model with who is friends with who. So there's 2 things we could do. We could learn general knowledge. We could learn transitivity, how male and female friendship works, how location affect friendship. We could learn all these very general type things. Or we could learn specific knowledge about who is friends with who, which particular group of people are generally friends with each other. Okay, so there's 2 different choices, one of which you could learn sort of general knowledge, and one of which you could learn specific knowledge. The specific knowledge will tend to be more accurate on the population, but doesn't generalize to different populations. So I can actually, so if you're Facebook and you have all the, the information for billions of people and you can just cluster them, it's probably what you should do. When we teach them, we try to pretend that we're learning general facts about the world, but we're typically not. Remember, how simple plus worked was that we just basically learned this clustered individuals and said this cluster is related to that cluster, and nearly all of them work the same. It's just that simple plus is the one we can explain what's going on. The general knowledge you'd expect to transfer better, but which is better depends on the goals and how success is measured. So depending on how we actually measure and what test set we're going to do, how we're going to measure it, depends on whether we're going to learn general facts or very just clustering of individuals. And so if we learn on one knowledge base and test on predictions on the other, we're not going to try to learn general knowledge. Okay, we're not going to learn that. We're just going to learn which people are related to which other people. Ideally, we'd like to try to do both. We'd like to learn about specific entities and general knowledge. Most of the current models do not do that. They either train on a fixed data set and try to predict on that data set, or else they try very hard to generalize the different domains. Ideally, we'd like to do both. All right. One of the problems with representing knowledge graphs is knowledge graphs only contain positive information. And the question then below is, how can we evaluate a prediction? Right, so we'd like to evaluate a prediction on a knowledge graph. So we'd like to make a prediction about, I expect this to be true. I expect something to be true. And so here are some test cases of FB15K, which is a common test set. Jade's North, what happens is we want to make a prediction. So what we do is we say, well, in the test set was Jade North plays position defender. So it's saying, Jade North, what position does Jade North play? And who plays position defender? Derby County has position this, and who has position defender? And if you think about answering these questions, you realize that they're not so trivial. You probably can, if you knew all the facts in the world, you could probably guess who plays position, what position Jade North plays. You probably don't know who Jade North is, but it's one of the test cases. And he's an Australian, by the way. But if you're asking who plays position defender, it's almost impossible to answer. Okay. So the common measures that you use, because it's hard to measure what the answer is, whether you're correct, it's common to use measures based on ranking, such as the mean reciprocal rank, hit at 1 and hit at 10. And then, by the way, you can actually ignore the probabilities. We can ignore the fact that there might be probabilities. Okay. It's not good. So there's a few problems with this. One of which is not good for answers which there's no answer or many answers. Who is the Pope married to? So everyone would answer that, say the Pope's married to no one, right? It's part of their job description as far as I know. But also you can't actually ask that question. This question never gets asked because it's not in the data set. There's all these questions you sort of can't get to. You can't actually ask when we have test cases like this. Another one is, who has streamed Drake's music? Well, it turns out that Drake gets hundreds of billions of streams on these things. There's probably more than 1 billion people who've streamed Drake's music, right? So if you're trying to guess, I'm thinking of someone who streamed Drake's music. Who is it? You know, you can't answer. You know, it's pretty hard to get a high ranking. Moreover, an omniscient agent who actually does very poorly on this. Suppose I know what position Jake North does. I'll go ahead and answer that question. And then the question here is, I'm thinking of someone who plays position defender. Who is it? And the omniscient agent can list off everyone who plays position defender in, but where they hit Jade North is sort of anyone's guess. You know, which Derby County has position. Well, Derby County actually has all the positions. It's just that by not reifying, actually the lost information, they're actually interested in who in particular plays position defender. So omniscient agents do poorly on this. The challenge is to design a good evaluation scheme. Log likelihood seems reasonable, but requires knowledge of negations. We have to know what's false, and we don't know what's false. There's a real challenge in here. All right. So if we have relations with multiple arguments, right, we could convert them to triples by reifying. So we could do that. However, that doesn't work. The reified entities have very, very few data points, the number of arguments of the original relation. I believe for the Samuel Ito data reified entity, there were only five facts in the data set, in the whole data set, in the whole knowledge graph. There are only 5 set facts about that, namely the start, the person, the position, the start, the end, and the number of games. They're the only facts about it, the only facts that sort of exist about it. Moreover, these people, because they have hammers that only work with big data, a lot of these test sets only work with, they throw out all entities with less than, say, 50 entities, and they've thrown out every single reified. So none of them actually been tested on reified arguments. So what we could do is to define embedding-based models that work directly with original relations, or we could just sort of allow them to be inferred by other relations. There's 2 different people who are doing research in those who are trying to build embedding-based models and those who are building models inferring from other relations. All right. So you can view a lot of these ones of distal, complex, simple, simple plus, is you end up with an embedding for the head embedding. You have a head embedding, a relation embedding, and a tail embedding. And somehow here you're going to combine 2 of these together. So both complex and simple plus, combine 2 of these windows. And there's just lots of these different windows for different embeddings. That's one way to view it. And a nice way of viewing it this way is that we can extend it to multiple arguments. We could extend it to 3 arguments or 4 arguments, as now we could have different window sizes. So one of the algorithms we have here is, there's lots of work by doing this, but one of the ways of thinking about it is trying to extend, it's thinking about sort of things like matrix multiplication, other things in different ways, gives us ways to extend it to 3 relations. And each of these windows is independently adds things up. Okay, so there's a hint about how some of these work beyond triples. All right. Oh, good timing. All right. So now I'm going to talk about a few other issues to talk about assumptions that people have made and that make good research problems. So none of the previous, so what can't any of the previous models do? So the thing is, embeddings give a measure of similarity. They don't give identity. But sometimes we need identity. Consider that you have a flight with stopover. There's a flight with stopover from A and B. Here we wrote it in sort of a logic programming language. a data log language. This is just the join of these two relations. There's a flight will start from A to B if there's a flight from A to C and a flight from C to B, right? And what happens here is that this entity in the first flight, has to be the same. It just has to be not similar. We have to worry about identity. You don't want to fly into someone saying, oh yes, you're leaving from another airport that's very similar, right? That's not very helpful to you. You say, oh yes, you're leaving from this airport. That's very similar to this, but it's not this one. You don't want that to happen, right? You have to worry about identity. But when we have embeddings, where everything's just an embedding, all of a sudden we don't have identity. So let's look at this example. In the room were Sam's mother, Chris's football coach, and a brilliant computer scientist. How many people were in the room? Well, some people look at this and say 3. Of course, the answer is at least 1. It could be the same person who's Sam's mother, Chris's football coach, and a brilliant computer scientist. Okay, so there's at least 1 person in there. It was also specified there was no one else. We know there are 1 and 3 people. Turns out that, we don't really have knowledge graphs. It's nice to have knowledge graphs that talk about, and there was nobody else. There's been work in the knowledge representation community that does it, but still not appear in knowledge graphs as saying, these are all the facts about it. It'd be really nice if there were, because it's actually very useful for probabilistic reasoning. So we need knowledge graphs to be able to state there are no more. All right. Similarity is weird. So identity is different. So this is sort of, people often get confused. These two are similar, but they're not the same chair. There's actually 2 chairs there. And I found a picture of our queen, who's celebrating something today in the news, apparently. And there's a picture of her when she's young and her when she's a bit older. And these aren't similar at all. These 2 people, they're actually the same person. So there's a notion of identity is not the same as similarity. Okay. It's actually it's a tricky problem. If you want to do count references in Seizure or Wiki or Google Scholar, one of the things they worry about is this reference the same paper as this other reference, right? So that's an existence problem, an identity problem. Is this the same as that? Was there a burglar here last night? It's an existence problem. Was there someone here who was a burglar? Was the burglar the same person as one of the people in the lineup? Right? It's an identity problem. So existence isn't a property of an entity. When existence is false, there is no entity. There's quite a bit of literature that talks about existence as a property of an entity. It all just seems like nonsense to me. 2 entities cannot be equal, have the same identity, otherwise there's only 1 object. And many methods, graph neural networks, which I'll talk about, and these other ones, which I'll talk about in a minute, assume this is already solved. We know what entities exist and what descriptions are equal. So as soon as we start using these other methods, we've already assumed that we've solved existence and identity. We sort of brushed those under the covers and said, oh, let's try and work here and let's sweep these under the rug and let's work on something simpler, simpler problems. All right. So here's a thing. Basically, there are symbols in the world, there are entities, and the house with the brown roof might be the same house as the tall house. So H1 equals H2. So quality corresponds to a partition of the symbols, and there are more than exponential in the number of symbols partitioned. It's the Bell number. So it grows faster than any exponential. Okay, so it's a really hard problem to solve, and so it's pretty much swept under the club. I know it's people who do sort of the open universe models. It's common to use just MCMC, you make up some and then you move them around. That's the standard way of doing that. There might not be a better way of doing it. And so it's a hard problem. We've sort of pretend it doesn't exist. And if we do it, we use MCMC. That's a good universal hammer. All right. So let's now talk about an older model called lifted graphical model. So lifted graphical model starts off with thinking about graphical models, as in Bayesian networks and Markov networks, etc., and then lifts them. So here's the problem. I put up this before. For those people who were here early, I put up this exercise. And And there are these 4 students and there are these 4 courses. I want to predict the grade of S3 on S4. And they have, it's not the only thing, we've never seen at C4 before. And the only thing we've seen about S2 and S3 is they have Bs in courses. They have the same course average. We've got a new course they've never seen, which we'd expect to do better. Well, it turns out you can predict better because they've got a B in one of these courses harder than the other. So what we can do is we could represent this as a belief network. And what you could have is you could have the intelligence of this, the grade of the student on a course depends on the intelligence of the student and the difficulty of the course, right? And when we observe grades, we can infer the difficulty of the courses and the intelligence of the students. And here's a model, and how the tables for this have, share the parameters amongst all of these. There's a parameter sharing. I believe this parameter sharing for relational models predates, what you might have heard about in convolutional neural networks, but it's the same idea. You're sharing the parameters. They're all developed in the late 1980s and early 1990s, these models of parameter sharing. All right, and if you do this, you'll find out that that 3 is expected to 50%, almost 50% chance of getting A in C4, and C's, and for student S4, they're more likely to get a C. You can play with the code here. I'll post these solutions. And what we do then is we can build the models. So there's these plate notations. What we're going to do is to build these generic models about what's going on here. So the intelligence of the student depends on, influences the grade of the students in the course and the difficulty of the course. Okay, and what happens is we're going to repeat this. It's like a plate that goes out from here. They're going to repeat this for all students. We're repeating I of S. For all courses, we're repeating I as, and we're going to map it out. We get something like this. Okay, we get something like this graph here that has the grade, that has the intelligence for each student, the difficulty for each course, and the grades for each student in course, but here I only included the observed ones. Okay, so these are called parameterized random variables. So for every student, there's a random variable I of S, and for every course, there's a random variable. For every course C, there's a random variable D of C. And for every course pair, there's a random variables S and C. And all of the instances share the same structure and parameters. So this is the basis of models that in the statistical relational AI community you've been working on. So if there are 1,000 students and 100,000 and 100 courses, the grounding contains 110, 101,100 variables. So the belief network here, the Bayesian network in this case, has 101,100 variables. There are 100,000 of these variables, right? There's one for every student course pair. But there are only 10 parameters. And so this is the basis for lots of the models that we're going to use. We use in statistical relational AI. In other models, the graph-based models, what we're going to do is we're going to assume the nodes are entities. So we're going to look at the grounding of the graph. They all exist and they're already disambiguated. So we're already presuming we've solved this. There are hyper edges between edges that are related. So we can do knowledge graphs, we do edges, but when we want to do higher level relations, we do hyper edges. And the function of the dependency depends on the type of the entity. So whether one person likes another depends on the property of the entity, not their identity. So it depends on the functions depend on the types. Markov logic networks and probabilistic logic programs, they define the factors with learnable parameters. And all the properties have a probabilistic interpretation. Graph neural networks are defined by how properties, embeddings of a node depend on its neighbors using some differentiable function. So in some sense, they're very similar, one of which is trying to have a probabilistic interpretation, and one of which is, so let's give up on all these, trying to interpret these hidden variables. Let's just try and do some differentiable function we can actually run gradient descent on. Okay, so that's the game, the different game that people play here. They're actually very similar in lots of ways. So you could pretend they're very different, but they're not. One just uses, as it tries to have a probabilistic interpretation, but one uses a differentiable function, doesn't care about the interpretation of hidden variables. All right. So GNNs are just choose the function to maximize predictive performance. The thing that I want to talk about is aggregation. So aggregation is how the neighbors affect the prediction of a node. And what we're going to do is we're going to what we typically do here is we're going to what we're typically going to do here is we're going to build a model about how the nations of different types affect the node, right? And but when there are unboundedly many neighbors of the same type, we need to combine them with some form of aggregation. Let's make this concrete. So what we're going to do, suppose you have a ratings of P&M. We have a ratings database just like we had for the movie lens. And what we'd like to do now is an interesting problem. We'd like to predict the gender or the age of the person from this rating. So it turned out one year I gave a grad course where this was sort of in the first assignment, and the whole term we tried to think of different ways of solving this problem, none of which worked. It ended up, my class project ended up as a paper in the Statistical Relational AI workshop, and sort of nothing really works here. So could you predict the age of me from movies I rated? So that's the challenge, right? And the trouble is that lots of the things that we think about doing just don't work. A lot of these work, the ones we've seen before, work by projecting to a low dimensional representation. So a vector representation, we project them down into a vector for ratings. We could project them down into the gender or age, but there isn't a lower dimensional gender or age representation. So if we try and represent a vector for a person, you can just memorize the gender. You don't need to generalize over it, right? You just memorize their age. So the vector for a person can just include those things. Okay, you can just memorize the age, we get no generalization. Somehow we have to aggregate over all of these other movies, and nothing sort of works at the moment. And most people say, oh, you can use whatever aggregation you want, and that's sort of infuriating because we don't know what aggregation we want. So here's what we could do is we could have the aggregator could be weighted formulae, in which case you end up with normalizing, you end up with either a sigmoid or a softmax, because I did that earlier. We had just formula, we have to average them, we have a product of all these terms, we take the logs and we take a sigmoid. All right, so that's the undirected model is Markov logic networks, and there's a directed analog which is called relational logistic regression. Everything is just defined in terms of weighted formulas. Probabilistic logic programs are directed models. They have existential quantification, which is a noisy OR. So you end up with there, the aggregator is a noisy OR. If you look at graph neural networks, they're unaggregated using the normal graphical models definition. They're undirected. And it's explicit. You have to specify what you want. You typically use sum, product, average, or max. So you have to sort of put in there, how am I aggregating all of these related individuals? So how am I getting from all the movies David's rated, how am I extracting one number from them? Okay, so they're typically sum, average, or max. So for average and max aggregation, the more data doesn't give better predictions, right? You'd expect if I've only rated one movie, if I've rated 1,000 movies, you'd think you could do a better prediction if I only rated one movie. However, for those ones that the average and max, essentially there's this one, the value that's the average value or the max value is all that matters. So more data doesn't help, which seems strange to me. For some aggregation GNNs and aggregation in Markov logic networks and probabilistic logic programs, so what happens is the sum can keep growing. Yes, the number of neighbors keeps growing, the sum keeps growing or shrinking, or just random chances, everything cancels out. So either the prediction doesn't depend on the neighbors, or the prediction goes to 0 or 1 as the number of neighbors goes to infinity. So either you're going to predict 1 or 0 as the number of neighbors goes to infinity, or the numbers cancel out in a very unstable way. So one way of testing and some of these models, so for Markov logic networks, this happens even if you don't make any observations. Even if you have no observations in the world, this happens. Which is, you just need the existence of the entities. And as the number of entities goes up, so does the probabilities all approach 0 or 1. And you could actually say, well, maybe I could see what works in these things. So here's the movie lens data. So this is the average, the probability that the age of the person is between 25 and 45, which is the most common age, as a function of the number of movies, and it doesn't look like any of the models that we've seen would theoretically predict. Okay, so maybe none of those work. Maybe none of them work. All right. One of the interesting things, do I have time for this? Yeah, no, okay. Some of these models let you fit polynomials. And here's what happens is you fit a polynomial for a small number of entities, and these two polynomials look really similar in lower numbers. But if you have a squared polynomial, what goes down must come up. And so one of these comes up at some other later figure, and you get into trouble. All right. So beware of those. All right, how am I going? Oh, good. 5 minutes. Good. All right. Another problem that we have is missing data. Here's an example. There's a drug that only causes sick people to get sicker and drop out of a study. So here's the people. Here's the placebo. Here's the base case. The case here. And here are the well people. Here are the sick people, and here is the people who took the placebo. Right. And then you have the people who took the drug, and you find out that what happens is these sick people got sicker, and a lot of them dropped out. And if we just ignore these sick people who dropped out, it finds out that it looks really well, because a higher proportion of the people who took the drug were well, who didn't drop out, than the people who took the placebo. Lower proportion of very sick. Okay, so if you actually if you ignore these things, you can't do this. So if you just ignore missing data, you say, oh, let's ignore the missing data, you get the exact wrong answer, right? It looks as though it works and doesn't work. People who do drug studies go to a lot of work to find out people drop out, why they dropped out. And that's really important. If people who drop out are ignored, it looks like the drug works. A larger proportion of those who took the drug are well. And we need to go beyond the data to missing data is missing. And things like EM actually work. So EM will fit any fiction you like to make about dropped out, including the correct one. But the correct answer is not in the data. You have to go beyond the data. So EM will work, and it will actually produce an answer, but it's just arbitrary as to where these people, where you haven't end up assigning these people who dropped out, whether you assign the very sick or well or sick, it's just completely arbitrary. Now, what happens is in relational models, almost all the data is missing, but we just ignore it. And somehow I think we do that to our peril. And so there's a huge problem in what we need to do in missing data, ignoring missing data. All right. All right, so now things don't work very well. And for people who study machine learning, the solution to poor prediction in machine learning is you collect more data, right? To hell with building better models, just collect more data. It almost always works better than improving your model. Just collect more data, particularly with universal function approximators. So can we always collect more data? All right. So what happens is while knowledge graphs and relational databases might be huge, there's often very little data about individual entities, right? So we often have individuals, there's very little data about them. And I'm going to claim that's inherent in the world. It's not a property of a data set, it's actually inherent in the world. So here's an example. SNOMED CT is a medical ontology of clinical terms. So it actually defines about 250,000 clinical terms and about 100,000 concepts of what could be called diseases. 100,000 is an interesting number because it's about the square of it's about the population of the Earth. It's about the same number as the number of people on Earth. For almost every pair of these diseases, for almost every pair of symptoms, no one in the world has both. Right? If you give me two arbitrary diseases, no one in the world has both of them. Right? Although lots of people have pairs of diseases, there's just too many pairs to cover all the people. And if you get to higher level comorbidities, there's just no one in the world who has them. So we can't learn these just by throwing big data about them. There just aren't enough people, right? There aren't enough people on Earth to actually, we could get all the Facebook people, They don't have enough data. They can't learn this, the interaction amongst diseases of all these diseases. You need some other way of combining things. Here's another example. Finding minerals to build batteries will help fund climate change. However, for all mined commodities combined, for all of these commodities combined that are mined, there are fewer than 100,000 high-grade deposits. And these are complex, and 100,000 is not really big data, particularly as these are actually about all mined commodities. For some of them, like cobalt, there's actually one. We actually know about one high-grade deposit of cobalt. And we also know that the new ones are not like the undiscovered ones are not like the known ones. So we sort of can't just throw big data at this and expect it to work. Reified entities have very few facts about them, and there's this long tail of entities about which we know very little. So there's this long tail of entities. So we can't just throw big data about it. Somehow we have to build models. Somehow we have to build models in here. All right. All right, good. So another field, there's just a new book out. The new book out is about lifted inference. Let's explain what that is. So before we know anything about the entities, they're indistinguishable, so they should be treated identically. That's called exchangeability. The names can be exchanged and the model doesn't change. If you're a Bayesian, the probability depends on what's known. It's called conditioning. You have your uncertainty, you condition about what you know. So the entities about which you know the same thing should be treated the same, right? So entities about the same information should be treated the same, just arbitrary names. If I tell you a student 1, 2, 3, 4, if I tell you a fact about them, or student 7, 8, 9, I tell you the same facts, you have the same beliefs because you don't know anything about them. All you know is their ID and their properties. And that provides symmetry that exploited in so-called lifted inference. The game we play in lifted inference is to exploit that symmetry that's inherent in there. And we have a book that came out last year in MIT Press. It's an introduction to lifted inference. But that's what it's about. It's about this idea of exchangeability, that when you're conditioning on things, entities about the same, you update your belief based on your information, based on your knowledge. And if you have the same information, you're going to have the same updates. All right, let's conclude here. Because I want to leave lots of time for questions. So one of the things I didn't talk about is I think what's happening is in the field, we're overfitting the standard data sets. The next person says, oh, I can beat this on this data set even without necessarily reading them. We need better evaluation metrics. I think we need one that an omniscient agent should do very well on. If you actually know the answer, you should do well on the evaluation metrics. All these methods on ranking do not have that property. Even if you knew the right answer, you do not do well on them. We sort of want to do, log likelihood seems sensible. We don't have negative knowledge. We need better ways to incorporate prior knowledge. So part of this negative knowledge is prior knowledge. Turns out Wikidata has almost complete knowledge about celebrities. So if you want to look up something in celebrities, Wikidata has 50,000 facts about Justin Bieber, for example. So somehow it'd be nice if you could tell your system that. But however, the people in Wikidata is not a random sample. You can't generalize to other things. So a lot of these cases we're building are based on Wikidata or Freebase or one of these other knowledge graphs. Wikidata is probably the best one. It's the best, most curated, up-to-date one. But we still need other meta information about prior knowledge on it. If you want to predict the properties of entities and the relationships, they're actually different problems. So if we want to predict relations, we typically go into a lower dimensional representation, and we do that. And predicting properties of entities, we normally do something different. Methods that work for one often do the others, but it's often not explicit in what you do. If you read one of these papers, you'll find out that they just say, here, I can do this better on this data set. And the data set typically tests either predicting properties or predicting relations, not doing everything together. So somehow we need to be much more careful about predicting these things. Because going to lower dimensional representations is a good idea for predicting relations. It works, but doesn't help for predicting properties. All right. Cool. We need better models of aggregation. I talked about aggregation, so we still don't have any good models of how neighbors should, how I should be my age could be predicted from the movies I watch. We need to take existence and identity of entities more seriously in general learning models. We need to model missing data, and that's actually a causal problem because it's not in the data. So the missing data is not part of the data. We have to model it somehow. And what I'm excited about is there's lots of environmental data that's coming. So there's lots of data that is being published in the environment that is relational in nature. We need to deal with time, ontologies, causality, big data, but basically there's small amounts of data about almost everything. But the overall is big data. We're working on a data set where the water pollution in Europe and time series of 20 times, 50, 60 time series for each element was a typical data point for one particular location. So the question is, will you step up the challenge? There's still lots to. I think it's an exciting area, even though I've sort of given lots of problems rather than an overview, lots of solutions. All right, thank you. I can see that.
Great, thank you, David. We'll clap. Maybe we'll virtually clap. Fantastic. Oh, that's great to have like a summary at the end of all the problems and challenges. I was trying to think a thing to ask about. So yeah, if there's questions from the audience, please like raise your hand, or if you can get to a microphone, please go ahead. I have one as well, but okay, Malik has a question there. We'll also have some in the chat. So Malik, if you can speak.
Yes, thank you for the great presentation. I have a very general question. So you presented uncertainty through probabilistic reasoning. So what is your take of using possibilistic reasoning instead to model some of the problem you listed, like for example, aggregation or prediction?
Okay. I think we're going to do decision. I think one of the ways of viewing possibilistic logic is you have disjunctive. I'm uncertain about the probability. But if you're uncertain about the probability, then they sort of map it in some logical form. But I think if you're uncertain about the probability, you should reason about it in the same way as you reason about other uncertainty, which is in terms of probability. So in fact, that's what Bayes did, as Bayes' thing was saying. We can actually reason about probability by having a probability over the probability. And to me, that seems like we don't need the possibilistic logics at all. But I like diversity. I think we can only survive, we can only work doing research if lots of people are doing lots of different things. And then we find out what actually works in the end. So I'm glad you're working on it. I'm glad some people are working on it. And I think it's important to work on it. It's awful if we just get stuck into one paradigm and everyone does that, because then we'll know we'll fail. So we want diversity in what we're doing. But to me, I think the Bayesian arguments, to me, seem more compelling.
Thank you.
Thanks. So in the chat, looks like there's a question from R. Cohen. I assume that's Robin Cohen, Waterloo, I'd be wrong. I don't know if you can see that. She was saying, they're pointing out the picture you had of the Queen. One was the picture of her when she was 7, or a painting of her when she was 7, and one when she was, one when she was 97. So if you specified the level of detail, the age, would you be able to then identify them and say they're
the same person, but they're not identical.
Not identical.
So I think so basically they're the same person.
Yeah.
Right. So that's right. The point here is that you have identities are an interesting problem.
So is that a different relation then? You'd add a different, because we'll just think of it as another feature. We just add another column to our table for machine learning. But how would you do that here?
Well, no, these are actually the same person. This property of this, the picture is different, but the person's the same. This is the person who's the person when she was a little kid, say 7 or something, and the person when she's now recently. So the person's the same, right? Whereas you try and model these two chairs up the head are actually, there's 2 of them though, right? There's 2 chairs, even though basically identical. If I mix them up, you can't tell But there is a difference between identity and similarity.
So what about time though? Because maybe you could also say that too. This is the queen at different ages, and it is a different person. So how would you?
There's an ancient riddle that the Egyptians used to do. Is you had started off with a ship, and you replaced one board with the ship, and after a while, it is it the same ship? Well, of course it's the same ship. You only place one board, but you do it with every board. And then you still have the same ship, it all has all new boards. But then someone comes along with all the old boards and builds another ship with them, which is the same ship.
One real ship.
And well, it's an ancient Egyptian riddle. It's not. There's no real solution to it. That doesn't mean that we should give up on identity, because we'd like to talk about. I'd like to hold you accountable for your crimes you did.
Well, I guess it depends on the task.
You now argue that you're a different person.
Yeah. Because whether it's relevant to the task you're doing, for so if it's about movie prediction or something, like, is it relevant that this person is the same person? And yes, it is. And so you could.
Well, but a lot of these things presuppose that. So the graph neural networks and the Bayesian networks presuppose you've already said, I've identified this person. This is not the description of it. This is actually the entity, and we're putting an embedding for them or one of these. Yeah. Right, we've already identified the person. And we have an embedding for them. And here you'd have two embeddings, so there's two people. And here you might have embedding for the queen at 7 and the queen at 77 or 97 or whatever it is.
I was wondering, like, you're talking about embeddings. Sorry, and like, because it's interesting to hear that you think the embeddings can be used that way, on top of these triples and things. But so, because you're talking about identity. But I'm curious about identity versus similarity or proximity, because often machine learning requires like this search space, and how do you get that out of it?
Well, we have a vector, but basically these embeddings are the vector representation of entities.
Yeah.
Right. So the entities, they're just hidden, they're just latent properties, right? They're just properties that we're just going to learn. So, so we have these embedding representations of entities, and you get embedding representations of relations by projecting down into the lower dimension, to the properties of them. So it's a game. I think having a fixed length embeddings for entities of Canada and the relation and other things, this photograph seems strange to me. So this photograph might have an embedding for it. It seems as though the embedding for Canada and the embedding for this photograph being the same length seems to me to be bizarre. So what we're doing here.
Yeah, no, sorry, go ahead. Yeah.
Sorry. Go on.
No, I was wondering if you have embeddings then of the relations and your triples and that kind of thing, does that mean you can still use them as a search kind of direction? Like, because you're saying, well, they're not the same, or their identity.
These are embeddings. These are embeddings of relations.
Okay.
Right. So this one here says you have an embedding for the head, you have a tail embedding, you have an embedding for the relation. You have two embeddings for each relation. And so you can actually represent all of these in terms of these embeddings. You multiply 3 of them and add 2 of them in some way for each of them, and then you add up all these different windows. That's how a whole lot of these ones work. These sort of pure embedding ones work by just having embeddings of relations.
Yeah.
So that's how they work. If you have graph neural network, what they add to this is you have neighbors. Right? So you actually have to know relations that they're in. So actually you're not uncertain about some of these relations because they form the graph. And then you actually can use the neighborhood. But then you want to get the embedding for this node based on the neighborhood. But the neighborhood can grow indefinitely. So you need somehow to get one vector from an arbitrary vector size, and that's what the aggregation is.
Right, yeah, that's what you're talking
about. So I don't know how to solve all these problems. If I did, I wouldn't be talking about it. I'd be out solving them. They just seemed as though they're a lot of them are just ignored.
Yeah, no, it's good to raise them. And they got that set of questions you have at their end so people can kind of see that. And we also have the slides up after the video.
I will post the slides.
So. Great, yeah. Okay, I think we're up with time, so we'll thank you again, David.
Right.
That was great.
Thank you.
Lots of new ideas, and thanks a lot for the talk. And everybody else will have a nice lunch and see you back at the next things when they start.
Right. Thank you. Thanks for the invitation.
Thanks again. Yeah, thanks so much.
I can stay on if anyone wants to chat. No, I'll go.
Yeah, sure.
Might as well stop recording.
We can probably stop the recording, yeah.
Whoever's doing that. All right. I just had a quote I could put up. But anyway,